Hello and welcome. This video tutorial is meant to help with magnetic force problems. Now, we're going to be looking at three in particular. The charge moving through a magnetic field, the force on a charge moving near a wire, so we're going to have to figure out the magnetic field due to a current carrying wire and then find the force. Okay, and then the mass of the particle moving in a field. That means we're going to have to use the fact that a magnetic force is actually a centripetal force causing circular motion of that particle within a magnetic field. Let's begin. First question is charge moving through a magnetic field. So please go ahead and put your name in the program so that we can begin. Now, you notice you're going to be given different things. You might be given a field going into the page or out of the page. Remember, dots means the field is coming out at you in the positive z direction. X means the magnetic field is going into the page in the negative z direction. So here's what I notice. I notice a field strength of 206 millitesla. So I'm going to draw I'm going to draw the system here. So I'm going to draw those dots. So I'm just going to draw a few. I'm only draw all of them. Okay, and I have a charge of 2 electrons. Okay, so that's going to be 2 times 1.6 times 10 to the negative 19. That would be 3.2 times 10 to the negative 19. So that's going to be our charge. That's my velocity was 1.65. 1.65 times 10 to the 7th meters per second. Let me just double check. Yes. And the magnetic field strength is 206 millitesla. Which is 0.206 Tesla. So that's all my information. Okay, so the first thing I'm going to do is it says use the axes below, give the direction of the charge and the direction of the magnetic field, then determine the direction of the magnetic force. So in other words, basically use right-hand rule, okay, to figure out the direction of the magnetic force. Well, my charge is moving in the positive x direction. So there, your thumb goes to the right. Put the pencil in between your fingers. Your pencil points out the palm of your hand because this is a positive charge. My fingers are going to go into the page. So my field is going to go like this. My field is going to be in the negative z direction. That's into the page. And so if I do that, if I put my field, sorry. That is incorrect. Dots means out of the page. Sorry, positive z direction. That's out of the page. So what I would do is I would put my fingers coming out of the page, my thumb pointing to the right, and I can see my pencil tip is pointing straight down. So my force is going to be in this way in the negative y direction. My force is down. But in the program, you're going to have to put it like that. So I'm going to go to direction. I'm going to select negative y. So I've got my direction intact. Now I just got to calculate the force. Okay, and that's going to be easy. That's going to be easy. So the strength of force, I'm going to use the equation QVB sine theta. Now understand, when the velocity and the field are perpendicular to each other, which they are, then this is 90 and sine of 90 is 1. So it's just QVB. So now I'm going to use my charge, which was 2 times the elementary charge times the velocity times the field okay. And I'm getting 1.087 times 10 to the negative 12 newtons. And there we go. Hopefully you were able to get question number 1 correct as well. Okay, on to question number 2. Go ahead and put your information. Run the program. Now in this one, you can see we're given the electron flow, okay, to the left. That means that conventional current is going to the right. That means your thumb would go to the right using right-hand rule number 2, okay? You can see that my charge, the distance of my charge is exactly 7 centimeters from my wire. So I'm going to draw that. So my distance R would be 0.07 meters. Okay, now keep in mind, if the electron flow is this way, that means current, conventional current, goes this way. So put your thumb to the right. That means I would dip my fingers below the wire, into the page below the wire, and out of the page above the wire. So that would look like this. Into the page below the wire, and out of the page above the wire, okay? In a two-dimensional form, that's how it would look. All right, so what am I else? Let's see, what else am I given? Oh, you can see I'm also given the speed of the charge, so 8.16 times 10 to the 6. Okay, my charge is 79.9 nanocoulombs. That, of course, is the same as 79.9 times 10 to the negative 9 coulombs. Remember, nano is 10 to the negative 9. And I can also read this ammeter here for current. Okay, and I can see my current is about partway between 3.2 and 3.3. Now, it's not quite halfway, so I'm going to say maybe 3.23, 3.22. I'll go 3.22. So I have to estimate my current, my amps. All right, so the first thing we're going to do is using the distance from the wire, we're going to calculate the field strength. So we're going to go B equals mu naught I over 2 pi R. Remember, mu naught has a value, that's the permeability of free space. Its value is 4 pi times 10 to the negative 7 times your magnetic field, times your current, 3.22 amps, divided by 2 pi times your R, which was 0.07. Now, the nice part about this equation is this part always reduces. And so on top, you're literally multiplying 2 times 10 to the negative 7 times your current divided by whatever the distance is, 0.07. Okay, so I have a value of 9.2 times 10 to the negative 6. So that would be 9.2 micro Tesla. Okay, negative 6 is micro. Okay, so we got that. Okay, oh, and I'm supposed to enter it in micro Tesla, so that's good. So 9.2. Okay, now I got to calculate the force on the charge. So we're going to go QVB again. I've got my charge, 79.9 times 10 to the negative 9 times the speed, 8.16 times 10 to the 6 times the magnetic field, 9.2 times 10 to the negative 6. 79.9 times 10 to the negative 9 times 8.16 times 10 to the negative 6 times 9.2 times 10 to the Okay, let me try that one more time. 79.9 times 10 to the negative 9 times 8.16 times 10 to the 6 times 9.2 times 10 to the negative 6. Yes, okay, I am getting that. So I'm getting 5.998 times 10 to the negative 6 newtons. Okay, now last thing I need to do is find the direction of the field. So if I look here, remember the field where the charge is into the page. Okay, remember that? It's into the page. So if I do that, if I look, I'm looking at a charge that is going to be moving upward. So the charge is moving upward. So it's a positive charge. The velocity is upward. The field is into the page. So if I use right-hand rule, I put my fingers into the page. My thumb is up. My pencil tip is pointing to the left. Okay, to the left. So the force is directed left. But to the left would be in the negative x direction. Oh, it looks like up, down, right, or left. So left. Okay, and there we go for question number 2. That worked out good. Hopefully you were able to get question number 2 correct. Most times people will miss question number 2 is for forgetting to convert meters to centimeters to meters for the distance part of the magnetic field calculation, or forgetting to put the magnetic field in Tesla instead of millitesla and converting it from Tesla to microtesla. There's a lot of easy ways to make a mistake. Okay, on to question number 3. Now in question number 3, okay, we're going to begin. It says we're going to be determining the mass of a particle in a magnetic field. Okay, so let's begin. You're going to see the charge moving in a circle. Okay, so what are we given? We're given the charge. So my charge, I'm given the speed, the field strength, and the radius. So let's enter in all that information. So the charge. Okay, now don't enter any of that. That's, I think I may have accidentally just made a screenshot copy of whatever I was using at that time, but it's going to be different every time. So the charge Q is going to be 3.2 times 10 to the negative 19. The speed, in my case here, is going to be 8.6 times 10 to the 6. Okay, the field is 0.80 Tesla, so B is 0.88 Tesla. And the radius is 2.166. 2.166 meters. Okay, so using the information, calculate the mass of the projectile. Okay, so here's what we know. We know that a magnetic force is a centripetal force. What that means is a magnetic force of QVB equals a centripetal force of mv squared over r. You can see one factor of velocity cancels, and if I swap out, actually I don't want to swap out the radius, I'm sorry, I want to solve for r. So I get Q times B equals mv over r. So what I want to do is I want to multiply by this ratio of r over v, both sides, and that will give me the mass of the particle. So it's going to be RQB over V. So the radius, 2.166, times the charge, 3.2 times 10 to the negative 19, times the field strength, in my case, it's 0.88 Tesla, divided by the speed, in my case, is 8.6 times 10 to the 6. Let me just try that one more time. 2.166 0.2 times 10 to the negative 19 times 0.880. Okay, divide that by 8.6 into the 6. All right, I'm getting 7.09 times 10 to the negative 26 kilograms. It's about right for a particle size. Calculate the kinetic energy of the particle. Well, we just have to go 1/2 mv squared. So 1/2 times this mass times that velocity earlier, 8.6, times 10 to the 6, and then square that. So I'm going to go 8.6 E6, square that, times that mass, 7.09, times 10 to the negative 26, and then take half. Okay, so I'm looking at a kinetic energy of about 2.62 times 10 to the negative 12 joules. All right, let's enter it in and see how we did. So you have to go and enter answers. So your name first. My particle mass. Okay, particle kinetic energy. Okay, and it shows me that my calculations are correct for this as well. So hopefully you were able to get your questions 1, 2, and 3 right. If so, go ahead and submit your work. If you're having any trouble, then please make sure that you come see me between classes so that I can help you. All right, until next time, we'll see you.